Okay, so we've solved Schrodinger's equation for a particle in a box, where the walls of the box are just defined as the first and last x values that we've chosen to plot. So for plotting from 0 to 5, the particle is constrained between 0 and 5 on the x-axis here, which is currently in angstroms. And these walls are infinitely high energy for the box. The wave function has to go to 0 at the boundaries because of how we've defined our Hamiltonian matrix. But what if you wanted to confine a particle in a well with walls that were not infinite, so that it's possible to pluck that particle out of that well given enough energy? We're going to program that case into our Schrodinger's solver program here today. So I'm going to start off by, and we're going to be building onto the same program, and every different potential type we're going to make a new tab for in our tab control. So, all right, click on that, go to add page after, and we'll call this well. And for our well, we're going to need a mass for our particle as well. So I'll just copy that control to this tab. And then we're also going to need some parameters for the box. So the first parameter that we'll need is where is the center of the box going to be located along the x-axis. So center in angstroms. So is the center of the box going to be a 2 or 1, or where's this well going to be located we're trying to make here? We're also going to need a width of the box, which is also going to be in angstroms. How wide is the well? I guess I should be saying well instead of box, since we've already defined the box as having impenetrable walls. And finally, we'll need a depth. How much energy does it take to remove the particle from the well here? So our energy units that we've programmed everything in is inverse centimeters, because that's experimentally useful. So that'll be the units of our depth as well. And those are the 3 parameters that we will need. Okay, so we've got our other tab here. And in our program, we've got this case structure, which is linked to our tab. So this tab is here. And it's doing a different thing depending on which tab we have currently selected. So we want it to simulate for the box if box is selected, and well if well is selected. So I'm going to add a case after, because I've already named that tab. That's the default name here. So perfect. This is what's going to happen for our well. I am going to make this a sub VI at some point, but for this iteration, I'll just put it directly inside this case structure, what we're going to do here. So how do we make a function which is a well? Well, the value of that function is going to be, we're going to define it to be 0 if in any location that's not in the well, and then negative of our depth value if we're in the well. So what we're going to do is make a for loop. We're going to take our x values from our make x sub VI there, and we're going to check every x value to see if it's inside of the well or not. The way we're going to do that is with this comparison palette in range, and coerce is the name of this sub VI here. The middle input is the value that we're seeing if it's within a particular range. And then what is the lower and upper limit? What is defining where our box is? Well, if our center is at 3 and our width of our box is 1, that would be spanning from 2.5 to 3.5. In other words, the lower boundary of the box is the center minus one half of the total width, and the upper limit of the box is the center plus 1/2 of the total width. So we can program that in there. So where did our center of the box control go? Oop, Just move it to the other tab. So center plus 1/2 of the width. Divide the width by 2. And center minus 1/2 of the width. And those are our, that's our range there. Upper limit, lower limit. Okay. Let's clean that up. Okay, and then we don't really care about this coerce output here. What we care about is the true or false. If the number is within the range of the box, this case structure is true. If it's not, it's false. And this is what our potential energy value is going to be held within, because if we're not in our box, our potential energy is just 0. So I can wire this all the way to the potential energy input here. Just keeping things clean here. And if we are in the box, our potential energy is the negative of the depth. Those are our two cases. The mass of the particle is just going to be wired directly to this mass input. And the x values are still exactly what they are. And the dx we can also just wire straight across. We're not going to do anything to those. Just going to put it behind the, oops. Just going to stick it behind the for loop here. Okay. And I think this is working, but to check it, what we want to do is we want to just graph it and see what it looks like. So here's our x values. I'm going to bundle the x values with our potential as the y values. I'll make a new graph to look at this on. And then we can try to run it and see if it's working. So if we have a mass of 1, width of 1, center of 1, depth, we're going to need a deeper well to confine this particle here. So let's make that 1,000. That should be fine. Okay, so what do we have? Here's our potential here on graph 2. And we do have a well shape. It's centered at 1 like it's supposed to be. It has a width of 1.5 to 1.5. Has a depth of 1,000. I'm just going to run this continuously so we can check all these parameters. The width seems to be expanding right. The center changes right. The depth is changing. It's auto-scaling, so it doesn't look like it is, but if you look at the axis, it is. Okay, but then the weird thing is you might say, well, here's the wave function that it's solving for. Why does that look like that? And that doesn't look right. Why isn't the particle trapped in the well? Well, remember the way we're solving this is with this inverse power iteration, which we have this shift value on to shift 0 so that even though we're always finding the lowest energy eigenfunction, we can shift 0 to eigenvalue. We can always shift 0 to be some number that's something else, and thus we can make any eigenvalue the lowest energy eigenvalue and find the excited states and so forth as well. So you'll always find the eigenvalue that is closest to your shift. If you think of this actually has units. This shift is in inverse centimeters, so I'll put that there. And so what we're doing is we're currently shifted at 0, so we're finding some state of the particle at the top of the box. So it's, or at the top of the well, rather. So it's not confined inside the well at all. If we want to find the ground state here, then I'm going to shift to negative 2000, because that's at the bottom of the well, so we'll find the energy level that's closest to that. And indeed, we have what looks like our ground state here, with just this single lump. And we should be able to shift up and find the first excited state and so forth. There we go. And you can see that there is some tunneling into the walls of the box. The box is at going from 1.5 to 2.5, and we have a non-zero probability before 1.5 and after 2.5, unlike our particle in an infinitely high energy walled box. So seeing some differences here. Okay, that is particle in a single well. What if you had two wells? Because then you could see, for instance, the tunneling probability of going from one well to the other well. It's also a fun case to try. So let's add another tab here. We'll call it double well. We're going to need all of these same parameters, so just copy and paste all these guys. And we need a width and a depth and a position for each well now. So call that center 1, depth 1, and then gonna position all these kind of on top of each other. And we'll copy and paste all of that. These are now, these will be the parameters of our second well. And yeah, I kind of want these to be in order. So let's do this. And we still need a mass of our particle. Okay, here we go. That'll work. Okay, so let's gather all of our controls, wherever they might be. And let's make a new case on our block diagram. Add case after, double well, perfect. Do a for loop. So again, wire our x values into the loop. I'm just going to go ahead and wire our dx all the way across. We're going to need to wire our x values all the way across. And we're going to need a little bit more room. Our mass, where is our mass input gone to? Right here. Put this in here. Wire that up to the mass. Now we just need to calculate the potential. What is the double well potential going to look like? Well, first we're going to do a single well, and then we'll add the second well. So we're going to check and see if our x value is within the parameters of the box or of the well. So I'll copy and paste this whole little chunk of code here, since this is going to look the same. I'm not sure if this was actually any easier than just redoing it, but let's do our center. Plus or minus the depth of box 1 here. Whoops, not the depth. The width. 1/2 the width. There we go. clean that up. And get that wired up. Don't want any backwards wires. Okay. And so here's our case structure to see if we're inside that first box. How is this different than our single well case? Let's give ourselves even more room. Now we have sort of a logic tree that goes one step deeper. Okay, if we're in our box 1, it's not any more complicated. Our potential is just going to be the value of the depth of that box, or rather the negative depth of that box. However, if we're not in box 1, we're not necessarily at 0 because we might be in box 2. So we need to ask another question, and that question is, are we in box 2? So now we need to check, are we within the center of the second box plus or minus 1/2 the width of box 2. So there's 1/2 the width of box 2 plus the center. That's the upper limit. Let's take our x value here, wire that in here. I'm going to get rid of these labels because now they're just making it messier. Lower limit is center minus 1/2. Oops, don't want that one. Center minus 1/2 the width. That's the lower limit. True or false? So if we're within the second box, then our potential is depth, negative depth 2. Need to negate that. And now, okay, if we're in our first box, the potential is equal to the depth of the first box. If we're not, ask another question. Are we in box 2? If we are, our potential is negative the depth of box 2. And if we're not in this box either, then we're not in any box and our potential is 0. So you could nest a large number of case structures there for any number of boxes if you want. Okay, and then that's all we really need to play with here. So let's just test it. We're going to need our boxes in different locations, so let's try a box at 1 and a box at 3. There we go. So we have a box at 1, a box at 3. Because these are kind of close together, the ground state is, it's equally likely to find our particle in box 1 or box 2. And here's our energy level for that. And we could see things like what happens when we move these boxes closer together. Oops, I'm just going to put in some numbers so I can use the arrow keys to move them closer. You can see we get some tunneling. And these wave functions overlap. There we're actually finding a excited state. And look at that. You can see the energy is actually getting lower as these combine because we're going from basically a narrow box to a wider box. But it would be nice to see to superimpose the wave functions on top of the potential. So that's what we're going to do in the next video.